again, the product rule so far seems to be an unnecessary complication to things. For example, if you're asked to determine the derivative, I'll take an extreme case. You're asked to determine the derivative of this function, and the function is x multiplied by 3x minus 8. Every sane person in this classroom, and that's all of us, would say that f of x is equal to 3x squared minus 8x, and then just use the power rule in conjunction with the difference rule. This difference rule that we talked about seems like overkill, but the difference rule says that if you want to determine, I hate f of x notation. If you want to determine dy dx and y is equal to this, then you can find the derivative with respect to x of 3x squared minus the derivative with respect to x of 8x. Are you with me? Does that make sense so far? I mean, what you can also do is use, it's called the constant multiple rule, which says that if you want to know the derivative with respect to x of a constant times a function of x, you can take the constant multiplied by the derivative of the function. All of this, of course, is totally unnecessary. From here, you can just say dy dx is 6x minus 8. Am I correct? Okay. And this is just a formality here. That's the thinking that goes along with it. But where I started with this was saying that's what you would do. This top line that you can see is what you would do. You wouldn't use the product rule for b. However, there will come a time where instead of having b where y equals x times 3x minus 8, you might have that, x cubed multiplied by the square root of 3x minus 8. In which case, you can't bring that stuff together, so you have to use the product rule. Just a quick review here, though. The product rule is the derivative with respect to x of two functions multiplied together is the derivative with respect to x of the first function multiplied by the second function plus the first function multiplied by the derivative with respect to x of the second function. That's the product rule. Take a look over your work and see if you have any questions you would like me to go over. No?
Maybe 8.
Who's speaking? 8? This is an interesting question that we will delve into more tomorrow when we learn something called the chain rule, which is the chain rule, which we will learn tomorrow, is a all-encompassing rule that applies to the product rule, the quotient rule, the sum rule, the power rule. The chain rule is kind of connected to this. So if we'll not worry about g equals f, because I think that's throwing you off kilter here because there's no g. The reason why they're saying that, I guess I will explain it, is that to use the prime notation, this is the, and I don't like that notation, but this is the product rule with f times g, right? So what they are saying is if f and g are the same thing, then what this would become would be f times f. What's the derivative of f times f? Well, it would be f prime f plus f prime. Are you with me on this? Okay. So what they're saying is show that the derivative of a function squared is 2 times the function times the derivative of the function. Well, if I want to determine the derivative of f of x squared, then this is the first, and this is the second. So what I'm going to get is the derivative of the first times the second plus the first times the derivative of the second. But multiplication is an operation in mathematics it's called commutative. You can multiply either way and get the same answer. 2 times 3 and 3 times 2, they're both 6. And what that means is I could, just for sake of simplicity, write this as f of x, f prime of x, plus f of x, f prime of x. In other words, I have, Ethan, 2 terms here that are equal. So it's like having r plus r. I get 2r. And that means that the derivative with respect to x of some function of x squared can be found by taking 2 times the function of x times the derivative of the function of x. This becomes a very useful rule. That's what we were asked to show. This becomes a very important rule because if I said to you y is equal to that, what is the derivative? You have 2 choices here. What you could do, well, you have 3, but until I explain the third, you won't know what the third is. One of your choices would be to take this and write it out as a product of factors. And then from there, here's your 2 choices. You can use the product rule. Take the derivative of this times that, plus this times the derivative of that. Or you could expand that out, and nobody wants to expand it out. Or you could use this rule that says, and I'm going to actually present the rule to you in a different way. Remember that we said the derivative of the square of a function is 2 times the function times the derivative of it. Well, I'm looking here. I'm not looking at this mess below there. I'm looking at this. Okay? What I'm going to do is swing the 2 down in front. Drop 1 from the exponent, but then I have to multiply by the derivative of what's inside. So that's where this f prime of x comes in. So it would be 12x squared plus 4x plus 3. And that's the derivative, and you got it like that. You didn't have to use the product rule. You used some other rule that it's going to eventually be called the chain rule. Does that make sense? Okay. Any other questions? Okay, so we are going to be learning the quotient rule today. We learned yesterday that if you wanted to take the derivative of the following, and you don't need to write this down. I'm trying to set the stage here for what it is we're doing today. We learned yesterday that what you are not allowed to do is just take the derivative of the first term, which is 4x plus 3, and multiply by the derivative of the second factor, which is 8x minus 2. That doesn't work. We started off Friday by showing through an example that the derivative of a product is not the same as the product of the derivatives. We need a special rule. So if I did ask you to differentiate this, you wouldn't get that. Do you understand that what I did to get this stuff was I just differentiated each piece? And it's wrong. You would have to differentiate this times the second plus the first times the derivative of the second. That's what works. So what we are going to learn today is there is another rule if there's a quotient, and it's a very important rule as well. I'm not going to spend time today showing you that we need a rule. You're going to have to trust me. That if I told you, well, I can give you a quick example. Let's say we have y equals 2x over x plus 3. And I say, what's the derivative of that? Okay? If you said, well, you know, I think I'm just going to differentiate the top and differentiate the bottom. But do you see that that's how I got 2 over 1? Well, 2 over 1 is 2. What you're telling me is that the slope of every tangent to this function is 2, which means you're telling me it's a straight line, and this is not a straight line. Okay? It's a hyperbola. It's got curves to it. So you are not allowed to just differentiate the top and the bottom. The rule is the following. We can use this bottom notation because it's very, very easy. This is the rule. The derivative of a quotient is found by taking the derivative of the top multiplied by the bottom minus the top multiplied by the derivative of the bottom over the bottom squared. Now, if we compare that with the product rule using similar notation, this is the product rule, right? So you'll notice something. The product rule has a sum here. The quotient rule has a difference. The other thing you will notice is that a sum is a commutative property. You can add in either direction. You know, 4 plus 3 is 7. 3 plus 4 is 7. Subtraction doesn't work that way. So you want to be very careful. Although you could very easily take these two terms and swap them and get the same derivative because it's correct. There's nothing wrong with that. It would just be you're remembering it in a different form. You cannot swap these. It's got to be derivative of the top, then times the bottom, minus the derivative of the bottom, then times the top. And there's all kinds of other notations you could use. The notation that I like, the ddx, is the most cumbersome, I think, here. It's the most convoluted, the messiest. So the derivative with respect to x of f of x over g of x is the derivative of f of x times g of x. That's the derivative of the top of the function divided by the bottom, minus the top, f of x, times the derivative of the bottom over the bottom squared. And I'll just show you a quick proof here. If you start off by defining the quotient to be capital F of x, this is what we want to differentiate. And I do exactly that, except I'm going to cross multiply first and rearrange for f of x. So I take this and I write it as f of x equals. And now I'm going to differentiate it. But when I differentiate this, the left-hand side to differentiate is easy. It's f prime of x. The right-hand side, I have to use the product rule. And I don't want you to just be passive about this. I want you to look at how I got that line from the previous line. I took the derivative of the first, which is capital F of x, times the second, which is g of x, plus the first, which is capital F of x, times the derivative of the second, which is g prime of x. And now what I'm going to do is I'm going to rearrange for this term. Capital F of f prime of x times g of x. And when I rearrange for that term, I, of course, get f prime of x minus capital F of x g prime of x. And this is very similar in philosophy to the proof I showed you on Friday for the product rule. I don't claim to be the person who discovered this. I didn't think of this. Somebody worked long and hard at trying different things and just to see what the consequence was, and somebody stumbled upon this proof. So don't forget, what I want to know, if capital F of x is f over g, I want to know capital F prime. I want to know what the derivative of a quotient is. And capital F is a quotient. So I'm going to divide both sides by g of x. And then I'm going to replace this capital F of x with f over g. And it gives me this. Now where do I go from there? Well, I would like to clean it up, and I have a complex fraction. I have a complex fraction, this f over g on the top, so I'm going to multiply the top and the bottom by g of x, just to get rid of that complex fraction. And when I multiply g of x by f prime of x, I get f prime of x g of x. When I multiply this mess by g of x, the g of x cancels, so I'm left with f of x g prime of x. And on the bottom, I have g of x times g of x, which is g of x quantity squared. And remember that f, capital F, is f over g. So f prime, capital F prime, is f over g prime. So that's one way that you could prove the quotient rule. And again, you get the post-secondary. Your profs will be teaching calculus through proofs and theorems. But let's put this into practice now. Much like the product rule, the quotient rule is kind of a rhythmic thing. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. It's just a pattern that you get into. So dy dx here is going to be equal to 3 multiplied by 4 minus 5x minus 3x minus 2 multiplied by negative 5, all divided by 4 minus 5x quantity squared. So we're okay with that step? There is never any reason ever to FOIL out the bottom. We always want all of our expressions, and this is going to continue throughout the whole course, in factored form because we want to be able to simplify them, number one. And number two, we want to be able to tell what values of x make the top or the bottom 0. And I can tell that a 0 of the bottom is 4/5. And that's an important number in terms of the derivative. That we won't worry about why it's important just yet, but it will be an important number. We do want to simplify the top. Since the top is just a series of linear things multiplied together by constants, it's to our advantage just to multiply this through. We get 12 minus 15x plus 15x minus 10. A lot of negatives to watch out for there. All right, if you wanted to, you could just do that. This 15x minus 15x on the top is a very frequent phenomenon. It doesn't have to be 15x, but a lot of the time when you clean up the top with the quotient rule, you don't end up with any variables on the top. You usually end up with just numbers. Well, not usually. A lot of the time you end up with just numbers. So we have 12 minus 10. The derivative is 2 over, and I forgot my squared here. The derivative is 2 over 4 minus 5x quantity squared. Very basic numerical response question. The derivative with respect to x of, what was it? 3x minus 2 over 4 minus 5x is equal to a over b minus cx quantity squared. What are the values of a, b, and c? So you have to find the derivative and put it in that form. Any questions with that first example? All right, let's take a look at the next one. So we have 2x squared minus 2x minus 12 over x minus 4. So derivative of the top would be 4x minus 2. The bottom is x minus 4 minus a really common mistake, especially when you're starting out, is to put plus instead of minus. So minus the top 2x squared minus 2x minus 12, multiplied by the derivative of the bottom, which is 1, over x minus 4 squared. And although this isn't a difficult question, I'd like to take a breath here and just take a look at my work to make sure that I got it right. Derivative of the top looks fine. Bottom is good. Yeah, we're good. So now we want to simplify this. Now, I suppose we could work on factoring this, but I would put it to you that I think it's quicker to just FOIL this out. And in fact, just to save us a little bit of heartache here, I don't think it's that big of a deal to FOIL it out. And that 10 is wrong. I don't think it's that big of a deal to FOIL it out and just put what it is here. It's minus 18x, I believe. Is that right? So it's FOILed out correctly. Okay, so now we can take 4x squared minus 2x squared, which gives you 2x squared. We can take negative 18x minus negative 2x, which is negative 16x. And we can take 8 minus negative 12, which is 20. Yep.
Isn't negative 18x minus 2x 20x? Negative 20x?
It's negative.
Oh, okay.
Are we okay now?
Yeah.
You sure?
Yeah.
Okay. So are we solid on this, you guys? Okay. Now we always want to, rational expressions are huge in this course. When you get an answer that's a rational expression, and this is, you want to ask yourself if you can simplify it. And the only way to simplify a rational expression is for you to factor everything completely to see if you have a common factor which can cancel. So this is just my exploration over here. And I better not do that. That seems to suggest that it's not important to officially factor it. We need to factor this. I can take a 2 out, and I get x squared minus 8x plus 10 over x minus 4 squared. And then I would say, is the top factorable? That is to say, are there two numbers that multiply to give 10 and add to give negative 8? And the answer is no. I don't think. It's been a long day, but. So our efforts here were not futile. They led us to the conclusion that this is probably okay for an answer, because we can't really factor anything any further. Any questions with 2 or B or whatever I've called it? All right, let's take a look at 3. Of course, we need to rewrite this as x to the half minus 4 over x to the half plus 4. Invariably, there's going to be a student or two that says, well, maybe we should try rationalizing something first to see if it becomes simpler. It won't, okay? You're just going to find yourself going in circles from one complicated expression to another one. So I have to use the quotient rule. And this is where things start to get a little more interesting. dy dx is the derivative of the top. And when you write this stuff out, I think it's really important to keep things organized nicely. Let me show you what I mean. When I move that half out in front of the x, I'm going to have 1/2 x to the negative 1/2. Okay? But I would rather have it written this way. Not always. Sometimes it won't matter. And in this case, I don't think it really matters. But that x to the negative 1/2 is on the top. Okay? So I'm putting it up with the 1. You don't have to do this. It's not crucial. But I like to keep things kind of organized to begin with. Multiplied by the bottom, which is x raised to the half plus 4. And then I have minus the top, which is x raised to the half plus 4, multiplied by the derivative of the bottom, which is 1/2 x to the negative half. And of course it's over x to the half plus 4, which is the bottom quantity squared. I have a feeling that this should be a minus. So again, I'm always checking over my work, and you should be too. I don't mean you should be checking over my work. You should be checking over your own work, right? So derivative of the top is fine, times the bottom minus the top times the derivative of the bottom. Now this is a visual thing that you're looking at here. You need to recognize that there are two terms on the top. You have this term minus this term. That's what you have on the top. And they both have a common factor of 1/2 x to the negative 1/2. So we're going to factor that out. I can factor out 1/2 x to the negative 1/2, and then I have left in brackets, I'm going to have x to the half plus 4 minus x to the half minus 4, but I'm subtracting the x to the half minus 4. So you're subtracting, you've got to be careful with those brackets, right? This is over. This is what I meant by keeping things in line. The whole thing is over, which means that 2 is really on the bottom of the whole thing. X to the half plus 4, quantity squared. We're almost done. All I need to do now is recognize that this x to the negative half can be written on the bottom as x to the positive half. And I want to spend a minute explaining why we're allowed to do that. Because you're not always allowed to just take something on the top with a negative exponent and throw it on the bottom. We are allowed to do it because on the top, the thing that's in the negative, that has the negative exponent, is an entire factor of the top. It's being multiplied on both sides. If there was plus, if it was x to the negative half plus 8, you can't move that x to the negative half to the bottom. The other thing I want to, of course, include is the x to the half plus 4, quantity squared. And then I want to put on the top 8. And I'm getting 8 because I'm saying x to the half minus x to the half is 0. And then what I have is 4 minus negative 4. Well, 4 minus negative 4 is 8. And my 2, which for some reason I didn't write. And finally, you can take that 8 over 2 and write it as 4. Right? 8 divided by 2 is 4. So the derivative will be 4 over x to the half multiplied by x to the half plus 4, quantity squared. And that's it. Take a look over our work there. Does anybody have any questions on that one? Okay. So if we knew the chain rule, there might be a simpler way to do this problem. But we don't know the chain rule yet. So you're going to have to use the quotient rule. Again, I'm going to revert to the dy dx notation. The derivative of the top is 0 because the top is a constant times the bottom we don't really need to write anything there because we're multiplying it by 0, so like who cares? It's going to be 0. Minus the top. And now we have to multiply by the derivative of the bottom. But the bottom is a product. So we have to use the product rule to find the derivative of the bottom, which means we're going to be referring to the first part of the bottom and the second part of the bottom in finding the derivative of the bottom. So Make sense? The derivative of the first would be 2 times the second is 4x plus 1 plus the first, which is 2x minus 3, multiplied by the derivative of the second. So this is d top. This is bottom. Of course, then it's minus top times d bottom. But of course, it has to be over the bottom squared. And when we're squaring, a times b quantity squared, you square a and you square b. Does that look okay? All that remains here, it's really not a difficult question once you get past the organization of it. All that remains is for you to figure out what all of this is, right? There's a little bit of algebra in here, and it's not that difficult. It's negative 5 times, what do we have? We have 8x plus 8x. We've got 16x in there. And we have 2 plus negative 12. 2 plus negative 12. Why can't I think? Negative 10? Okay. I do not, by the way, since this is 0 over here, this red line up top is the whole top of the whole thing. I do not want to multiply that negative 5 in. I want things in factored form. If anything, I want to factor a 2 out of this. I can take a 2 out of the 16x minus 10, and the negative 5 becomes negative 10. It's 8x minus 5, and it's over 2x minus 3 squared and 4x plus 1 squared. Any questions with that example? Yeah.
If you got like a same factor on the top as the bottom, you just cancel?
Definitely. And that's one of the reasons, Bryn, we want it to be in factored form. Like maybe, it would be pretty obvious that it's not the case, but maybe when you factored that number out, you're left with a 2x minus 3, in which case you can whittle things down. But we want our final answer written this way because there are these things, and I find that if I just introduce this notation to you here, later on you'll go, oh yeah, I remember it. There are these values of x which we call critical. They're critical values of x because they do one of two things. They make the derivative equal to 0, like 5/8 does, because if the top of that expression is 0, the derivative is 0. Or critical values of x are also values of x that make the derivative not defined, like negative 1/4 and positive 3/2. And it turns out that in places where the derivative is equal to 0, and also in places where the derivative is not defined, may be something special going on. May not be. I call the critical numbers the suspects. You have to line them up against the wall and look at them individually to decide if they are really important or not. But you need to be able to find them first. What they are important for is not important right now. Okay? You won't worry about that. Determine the slope of the tangent to this curve at this point, 2 comma negative 1. So the function is y equals x cubed minus 5 over x minus 5. What is it you need to know? Is this our final example? Okay. What is it you need to know to determine an equation of a line, in this case a tangent line? Well, the first thing that you need to know is a point. Well, since this point 2 comma negative 1 is on the curve, and the line is tangent at that point, this point is on the tangent line. Right? Whatever the curve looks like, it doesn't really matter. If this is 2 comma negative 1, the tangent line looks like that. That point happens to be a point on the line. We also need to know the slope of the line, the slope of the tangent line, but that's equal to the value of the derivative at that point. A couple of you made the mistake on the quiz of thinking that the slope of the tangent is the derivative. And I want to make sure you understand what that mistake involves. Once the slope is determined, you put the slope along with x1 and y1 in here, right? What a couple people did is they didn't put the slope here, they put the derivative. So they had a bunch of x's in there. That's not the slope. The slope is not the derivative. The derivative is a formula you use to find the numerical value of the slope. Okay, so let's find the derivative. dy dx is 3x squared times x minus 5 minus x cubed minus 5 times 1 over x minus 5 squared. And again, I get going on autopilot. So at the end, I'm talking, I'm thinking, I'm writing at the same time. At the end, I want to check my work, and you should do that too. Derivative of the top times the bottom minus the top times the derivative of the bottom. I think it's okay. Now, we've talked about this before. You don't want to simplify this. Well, I shouldn't say you don't want to. You don't have to simplify it because you're just putting a number in for x. And really, for my advice to you is, as a student, don't simplify it because as soon as you start to, you could make a mistake, right? The more work you do, the more risk there is of a mistake. And you should have learned by now in this course, nobody's mistake-free. You're going to be making them from time to time. So, I would just put the 2 in and do this kind of in pieces. I would do it on paper. I wouldn't do it in my calculator first. I would say that 3x squared is 12, for example. When I put x equals 2 in and I square 2, I get 4 times 3 is 12. 2 minus 5 is negative 3. Uh, 2 cubed is 8. 8 minus 5 is 3. Times 1 is still 3. And this is over 9. Because 2 minus 5 is negative 3, and negative 3 squared is 9. So let me run those numbers through my brain again. 12, negative 3, 8, 3, minus 3. We're good. I think it's okay. Yeah?
Should you put n tan there when you're summing it in instead of the derivative?
Oh, yeah, you know what? Or, you're right, I should. I shouldn't say dy dx anymore, because at this point I'm finding a specific value of the derivative. I should either put m of tangent, or f prime of 2, or what I just added. Yeah. So is that negative 39 over 9, which is negative 13 thirds? Just get somebody else to agree on that, negative 13 thirds? Okay. Okay, so here's where we're at. The point is 2 comma negative 1. The slope is negative 13 ninths. We put it into our point slope formula and get y minus negative 1 equals negative 13 ninths, x minus 2. Personally, I would just multiply both sides by 9. What did I do?
It's 13 thirds.
13 thirds. Thank you. Right. Personally, I would just multiply both sides by 3 here. I wouldn't carry that 13 thirds through as a fraction because we want our final equations in the ax plus by plus c form where there's no fractions. So let's get rid of them at the outset, which would mean 3y plus 3 equals negative 13x plus 26. Move everything to the left side to get 13x plus 3y minus 23 equals 0. How's my numerical arithmetic there? Is that okay? And that's the equation of the tangent. and that's the quotient rule. So tomorrow we will learn the chain rule, which will allow us finally to find derivatives of things like that, or that. And you don't know how to find the derivatives of those things yet. As soon as we have an exponent, the only way you can find the derivative of the top here is to FOIL that out. You don't know what the rule is, although Ethan's question about number 8 kind of leads us to suspect what it might be. So there are some questions that you're practicing today with the quotient rule. I'm also going to give you your first assignment, which is due Wednesday. It's 2 questions. One is to find the equation of a tangent. And for question 1, you should be able to find the derivative. I better make sure before I say that. Yep. For question 1, you will be able to find the derivative without using limits. Okay? For question 2, it's a rate of change question. I can show it to you. Everybody's got a slightly different question, but so question 1, determine the equation of the tangent to this function at x equals 5. There's going to be a lot of fractions involved, because I don't know what you're going to get when you put 5 in for x. You're going to get negative 23 halves for the y coordinate. But the second one is a water tank question where you're asked to find the instantaneous rate of change, which means you either have to use limits, in this case as t approaches 10 minutes, of that expression minus that expression at 10 minutes, all over t minus 10, or wait until the end of tomorrow's lesson, where once you know the chain rule, you can find the derivative without limits. But I want to make it clear here that the answer to this question is the value of the derivative at that time. But you don't know how to find the derivative yet without using limits. You would learn tomorrow. And your assignment's due Wednesday. So you have a decision to make, right? And it's due Wednesday. It's not, oh, can I take it in Thursday? No, it's due Wednesday. So I will hand that out to you, and you have those questions outlined in your handout to complete. And I'll come around and I'll help you out.